Assalamu alaikum and welcome back. So we'll continue the previous lecture where we were studying about the elementary signals, and you understand that these elementary signals are very important because they are building blocks for constructing many more complex signals. So this was the generalized equation or expression for the continuous time complex exponential signals, and we know that there are two important parameters here. One is C and one is A. So we have studied about the first case where we said C and A are real. So you understand, depending on the values of these, x of t can exhibit different characteristic, right? So let's take the uh, second case, right? So we said when both C and A are real, we have real exponential signal. So in this case, if the real part is 0, right, then because it's 0, so replacing uh, the value of the sigma here, it will result into a constant signal, because anything multiplied by 0 will result into 0. So this will be a constant signal as shown here, right? So if sigma is 0, then we have a constant signal, and amplitude of this signal will be equal to the value of the C. So that means the value of this signal equals to C. So if C is positive, we have something like this, right? If C has negative, then you understand this is your time axis, right? And this is the value of the x of t. Again, you understand that because we are dealing with the time domain, and also in time domain we have two type of independent variable. It can be the time t, which is a continuous variable, and it can also be n, which is a discrete variable, or we say that it has integer values, right? So for this particular case, if C is negative, and in that case the resulting signal will have value something like this. So I hope you understand. Okay, so this is the third part for the case when both C and A are real. Okay, so the second part, right, in which we say when the real part of A is 0 and its imaginary part is j omega naught, and again we say that C is a real, right? So you understand, for the generalized expression, this one, this is the generalized expression, right? So in maybe let's call it case 1. So in case 1 we said, okay, both A and C are real. So in that case we had real continuous time exponential signal. So depending on the value of A and C, especially A, right? So if A is positive, in that case we had a exponentially growing signal. If A was negative, in that case we had exponentially decaying signal. And when A was A, which is because in this particular case A equals to, we assume that they are real, so that means the imaginary part was assumed to be 0. So in that case, when we had only the sigma or the real part, if the sigma was positive, it was exponentially growing. If sigma was negative, then it was exponentially decaying. And when sigma equals to 0, we have the constant or DC signal, right? So it can be positive if C is positive, and it can be negative if C is negative. right? So in this second case we say, okay, C is again real, but A is now imaginary. So when C is real and A is imaginary, and let we say that the real part of this is, because we say it's imaginary, so that means real part is 0, and we say, okay, its imaginary part is equal to plus minus j omega naught. So that means A equals to plus minus j omega naught. So if we replace this value in the standard equation, we get x of t equals to e j omega naught, right? And let we take c equals to unit, right? So if c is 1, that means for the generalized, right, I hope you remember, that is x of t equals to c e power a t, right? Now because in this case we say, okay, c is unit, so that means c equals to 1, and we say a equals to plus minus j omega naught, so that means x of t equals to, right? Now x of t is periodic complex exponential signal. For a signal, if we understand, for a signal to be periodic, it must satisfy the equation, that is x of t should be equal to x of small t plus the capital T, where capital T is the period of the signal. So if any signal satisfies this condition for all t values, right? For all t, right? So if x of t is satisfies this condition for all t values, then we say x of t is a periodic signal. Now for x of t to be periodic, right? So because value of x of t equals to j omega naught t, so let's put this in the equation. So that means if I replace t with t plus t, that means I have now x of t equals to e power j omega naught, right? And I replace t with t plus capital T, right? So if this is periodic, then it means that because if I expand it, I will get this expression, right? Now if x of t is periodic, that means this should be equal to 1. So that means e power j omega naught capital T should be equal to 1. So that means this is equal to 1 when, right? So then e power j omega naught equals to this, which is x of t, right? So that means x of t capital T plus x of small t plus capital T equals to x of t. So if this expression equals to 1, then we have the condition, which is this one, is satisfied. So let's check when this happens. So it will e power j omega naught t equals to 1 when omega naught equals to 0, because anything multiplied by 0 will result into 0, and anything power 0 will be equal to e power, in fact e power 0 will be equal to 1, and this condition is satisfied. So if omega naught equals to 0, then we say x of t will be a constant. Why? Because e power j omega naught t, so that means omega naught equals to 0. So when omega naught equals to 0, so look at this equation, then this will result into 0, so x of t will be, right, again if you write here, so this is your omega naught. If this is 0, then anything multiplied by 0 will result into 0, and e power 0 will result into 1, which is a constant, right? So if omega naught equals to 0, right, again we come to the topic when this will be equal to 0. So condition 1 is when omega naught equals to 0. When omega naught equals to 0, this thing will equal to 1. So when omega naught equals to 0, then x of t is a constant, and we can say it's periodic for any value of t. Okay, so again the second case is if omega naught is not equal to 0, in that case t will be equal to 2 pi by absolute of omega naught, right? So in that case we have x of t to be variable, right? So when t equals to this, whether omega naught is positive or negative, thus we say that e power j omega naught t and e power minus j omega naught t and e power plus j omega naught t have same fundamental period, because period equals to t, which is 2 pi by absolute value of the omega naught. So that means they both have the same period, right? So the continuous time complex exponential signals are periodic when the a equals to plus minus j omega naught, right? That means its real part is 0 and imaginary part has some value, which is this one. Okay, so that means it's a periodic complex exponential signal. So then we come to the thing that what is basically relationship between sinusoidal signal and periodic complex exponential signal, right? So you know that the periodic complex exponential signal has this expression, generalized expression. Previously we were not using phi, but in case of generalized expression we also include the phase or phi here. So the generalized expression for periodic complex exponential is e power j omega naught t plus phi, and you understand omega naught is the frequency and time is your independent variable, because we are dealing with the time domain. So time is here, and this is the phase. Okay, this is the phase of the periodic complex exponential signal, right? So using the Euler relation, also called Euler formula or Euler identity, we can express it into this thing, which is a real part and this is the imaginary part, right? So this is equal to cos omega naught t plus phi and plus j sine omega naught t plus phi. If this is e power minus j omega naught t plus phi, in that case we can say that the cos omega naught t plus phi minus j omega naught t plus phi, you understand, because cos is now, because you have just basic understanding of the even and odd function. So cos is even function of the time, that means cos, right, cos of minus theta equals to cos of theta, right? But sine is the odd function of odd function, so that means sine of minus theta equals to minus sine theta. So that's why, because the sign here is changed, here it was positive, here it is negative, but again you see there's no effect on the real part, because real part is even function of the time, whereas the odd part whereas the imaginary part, which is sine is the odd function of time. So that's why we have this, right? So this is how we can represent a complex exponential signal in terms of sinusoids, and I hope you already know that you have done these relationships in your mathematics course. Okay, so similarly, like we can express a complex exponential signal in terms of sine and cosine. So similarly, we can represent sine and cosine, which is in general we generally called as the sinusoidal signal. So complex exponential signal can be expressed in terms of sinusoidal signal. So that means we can also express a sinusoidal signal in terms of complex exponential signal, right? So that means a cos of omega t plus phi, right? So you understand a is the amplitude, uh, uh, omega is the frequency and t is the time, and phi is the phase of this sinusoid. So this sinusoid can be expressed in terms of the complex exponential signal. So it can be expressed as a by 2 ej omega t e power j phi plus, or you can also write it like you understand that basically a is like this. Maybe you're familiar with it. So this is a, then you say for cos e power j, right? It will be omega t plus phi, and plus e power minus j omega t plus phi. Okay, so and divided by 2, right? So if you simplify this, you get this thing. So this is how you represent a sinusoidal signal in terms of complex exponential signal, right? Similarly for sine, you can write the same expression, but here it will be minus, right? And also have, so that's for complex exponential signal in sinusoidal signal in terms of complex exponential signal, right? So this is the, and similarly you have done here. So that means based on this arguments, we can say, because complex exponential signal equals to real part plus the imaginary part, so that means if we have cos, right, omega t plus phi, so that means we can say cos is basically the real part of this complex exponential. Similarly sine theta, if I simply say, so sine theta, right, I call this whole as theta, so sine theta is basically equal to imaginary part of the uh, complex exponential signal, right? Because the complex exponential signal has real part and imaginary part, right? So that's the relation. So we can also say if I have cos this, so I can say cos is basically the real part of the complex exponential signal this, and similarly sine is the imaginary part of the complex exponential signal this. So I hope this gives you some idea. So if you have any, go through these slides, and if you have any confusion, so you can ask me in the live session. Okay, so then we come to the fourth case, right? So in this case we say that both a and c are complex. So when both a and c are complex, and we represent the c as a in the polar form, that is, you understand, to express complex number, we have two forms. We can say we have the rectangular form and we have the polar form, right? So in rectangular form, for example, z is a complex number, then we say okay, z equals to for example a, which is a real part, plus j, which is imaginary part, and b, right? So this is we call as rectangular form, right? So this is the rectangular form. that you know. So again, in rectangular form we have the real and imaginary parts, right, separate. Whereas in case of the polar form we have the magnitude. You understand how we calculate the magnitude. So we represent magnitude by the ABS symbol or these two bars. So these two bar means it's the absolute value, which is also called the magnitude. And how we calculate the magnitude? So to calculate the magnitude we say, okay, real square plus imaginary square whole square root, right? So this is how you calculate the magnitude. So to express the complex number in the polar form we need magnitude and we need the uh, angle, right? So how to calculate the angle? So let's represent angle by this. So angle of z equals to uh, tangent inverse, right, imaginary over real, right? So imaginary over real and taking the tan inverse will result into the phase or the angle. So to represent a complex number in terms of phase and angle, which is called the polar form. So in polar form we write like this. So this is the polar form notation. Okay, so in this fourth case we say both C and A are complex. So C in the polar form is this, because complex numbers can be represented in polar form also. So this is your C. And again A is in the rectangular form, so that means we have A equals to sigma plus j omega naught, and you understand sigma is real part and omega naught is the imaginary part. Okay, so putting the value here we get this expression, right? So okay, this is your C, magnitude of C, and then angle of theta or phase of C, and then we have this is A, so A equals to sigma plus j omega naught into T, right? So that means if I simplify it I get I hope you understand how to simplify it, right? So if I split it right into real and imaginary, so that means I can write this thing, right? I can write this thing as e power sigma t, right, and e power j omega naught t, right? So because this again e power j omega naught t, and again this e power j theta is multiplied with it, so that means we can split it like this, and then we can write this this is all are multiplied, so they have same basis, you see, and they both contain j theta and j, that means, right? So we can simplify it, we can write it like this. So that means the e power j omega naught t plus theta. So writing this in the sinusoidal form, because this is complex exponential, right? So this can be written inside sinusoidal form as previously discussed. So this will be equal to omega naught t plus theta and j sine omega naught t plus theta, right? So you see that C has some value, absolute magnitude of C, this has some value, and then this is, you see, e power, this one, e power sigma t, this is basically a exponential signal, right? Real exponential signal. So the resulting waveform will be if sigma is greater than 0, right? So if sigma is greater than 0, that means this signal will be exponentially growing, right? So if sigma is greater than 0, that means it has some positive value. So when we have even very small positive value, but t is increasing, you understand t has value from 0 up to infinity. So when t is increasing, that means this is exponentially growing signal, and this is your sinusoidal term, right? So that means when this is exponentially growing, so the resulting signal will be sinusoidal multiplied by the exponentially growing signal, right? So you understand how we are going to plot this signal, right? So you understand, because we have two terms here, that is the imaginary real term, this one, right? Cos omega naught t plus theta, this is the real term, and j sine omega naught t, this is the imaginary term. So this is this factor is multiplied both with this one and this one. So that means if sigma is positive, right? So this is exponentially growing signal. So we have exponentially growing signal multiplied by real, and then we also have exponentially growing signal multiplied by the imaginary, right? So that means the resulting signal, because this is cosine wave, right? So cosine wave multiplied by exponentially growing signal, so it will result into exponentially growing cosine. And this one again, sine term multiplied by exponentially growing signal, so it will result into a exponentially growing sine, right? So that means to plot this signal, we need basically two graphs, right? One for this one and one for this one. This is the generalized expression where we say, okay, when sigma is greater than 0, so this signal will be exponentially growing, and when sigma is less than 1, that is negative, then it will be exponentially decaying, right? But in fact, we have this generalized one. To plot this signal, we need two graphs, right? One graph to plot the time versus this signal, and one graph to plot the time versus this signal. So for example, this is your generalized cosine, right? Something like this, right? This is your cos, and again, right, this is cos theta, yeah, cos of, right? And if I plot a sine, then I have something like this, right? This is sine. Okay, so because we have two terms here, real term and imaginary term, so that means the resulting graph will consist of two waveforms, one for real, that is real versus time, and one for imaginary versus time. So because if sigma is greater than 0, then both of these terms will be exponentially growing. So this graph of this will be exponentially growing cosine, and graph for this one will be exponentially growing sine. Whereas if sigma is less than 0, that is negative, if sigma is negative, then the resulting, this will result into exponentially decaying. So to plot the signal, we will multiply exponentially decaying times the cos will be one graph, and exponentially growing times the sine will be another graph. So I hope you understand that to plot a complex variable, we need two graphs, one time versus the real part of that complex variable, and the other is time versus the imaginary part of that complex variable. So I hope this gives you some idea. So now let's jump into the second part of the complex exponential. So it's quite similar to the one we have done for the continuous time case. In this second part, we are going to deal with the discrete time complex exponential signal. So I will not spend much time on it, and I hope if you understand that one, so it will be quite straightforward for you, so you can go through it, right? So again, the generalized form for the complex exponential signal is x of n. You understand, n signifies that, or emphasizes that we are dealing with the discrete time signal. You understand, to denote a discrete time signal we use the square brackets, right? And to denote the continuous time signal we use the parentheses, right? So the continuous time case for the generalized form of the complex exponential signal was something like x of t equals to c, right? And e power j omega naught, right? Plus, in fact, okay, I can also write here sigma plus, you can also write sigma plus uh, j omega naught t, right? So that was for the continuous time case. So exactly similar is the representation of the generalized form of the discrete time complex exponential signal, which is x of n, like this. So I hope you can appreciate the difference between the notations of the continuous and discrete, right? So this can also be written as x of n equals to c e power beta n, where alpha is replaced by e power beta. So these are two different forms, like this one and this one, for the generalized case of the complex exponential signals. So again, depending on the values of the c and a, we can generate different uh, discrete time complex exponential signal, similar to the case of the continuous time. So when the case one we considered, there was the real exponential. So again, we can obtain the real exponential signal when both c and a are real, right? So you understand, when c and a are real, that means the resulting signal will be a real, right? You understand from the previous discussion on continuous time case that c is basically a scaling factor. Okay, so when these both are real, then we say, okay, if alpha is greater than 1, if alpha is greater than 1, so for example, if alpha equals to, right, uh, for example, if alpha equals to greater than 1, can be anything. Okay, let's take it to be 2. So when alpha is 2, so we say x of n equals to, and c equals to, for example, alpha equals to 2 and c equals to, okay, let's take it to be 5, because just it's a scaling, or even it's 1 or 0.1, whatever, it doesn't make, it's just the scaling factor. So we say, okay, because uh, x of n equals to c alpha power n. So by putting values, we say, okay, alpha equals to how, c equals to how much, 5, and alpha equals to 2, so 2 to the power n. So you can understand that as n increases, for example, n equals to 0, so it will be 2 power 0 is 1, then n equals to 1, 2 power 1 is 2, when n equals to 2, then it is 4, and so on. So you understand the resulting signal is basically exponentially growing or increasing, right? So when alpha is greater than 1, the signal is exponentially growing, which is shown here, right? The second case will be when alpha is between 0 and 1, right? So you understand, if something is between 0 and 1, that means it is positive but it has value small, right? For example, 0.5. So if you take a 0.5, alpha is 0.5, and then alpha is for example 0.5, so alpha square will be smaller, right? Square of the 0.5 will be 0.25, then cube will be again smaller and smaller and smaller. So that means you understand, this will be exponentially decaying signal when alpha has values smaller than 1. Okay, so again, the second thing is when alpha is negative but less than 1. So when alpha is negative and less than 1, So let's take alpha equals to be, let's take alpha, because we say alpha is, we're talking about this case. So alpha is less than minus, greater than -1 and less than 0. So for example, we say, okay, alpha is 0.5. So what will be the resulting uh, signal when alpha equals to -0.5? So you understand, because x of n, right, equals to, let's take c to be same. So let's take, okay, I write here, for example, c equals to, again, 2. So it will be something like 2 into minus 0.5, right, to the power n. So you understand, when n is even, this will be positive. When n is odd, it will be negative. Also, because with the increase of n, you see this is 0.5. So if you increase the n, its value will decrease, right? So that means when alpha is between -1 and greater than -1 and less than 0, the resulting signal will be decaying, right? So it will be exponentially decaying signal, and it will alternate in signs. Why? Because when n is even, the resulting signal will be positive. When n is odd, the resulting signal will be negative. But both, either negative or positive, in both cases it will be exponentially decaying, right? So I hope that gives you the idea. Okay, now the another case is when alpha is less than -1. So less than -1, you understand, will be like -2, -3, -4, and so on. So in that case, the resulting signal, because we are taking powers of the alpha, so for example, -2, if we take, okay, so less than -1 will be, say -2. So if it is -2, in that case it will be exponentially growing. But again, because there is minus sign involved, so that means for even values of n it will be positive, for odd values of n it will be negative. So that means the resulting signal will be exponentially growing. Why? Because its value is greater, less than -1. So less than -1 means maybe -2, -3, or whatever, right? So if you take square power of -2, it will give you, I mean, it will be exponentially growing. But because there is minus involved, so it will be alternating. So you see, the resulting signal is exponentially growing, but it is alternating in sign. Okay, so for even it will be positive, for even value of n it will be positive, and for odd value of n it will be negative. So in the second case, we assume that c is real and alpha is complex, and alpha equals to e to the power j capital omega naught, right? So in order to differentiate between the frequencies of the discrete time signal and continuous time signal, let's represent the frequencies of the discrete time signal using the capital omega, right? So for the case of the continuous time signal, we use the frequencies which were represented by the small omega, right? So it is similar to the case you have discussed for the continuous time, right? So the resulting signal will be, x of 1 will be equal to e power j omega naught, and where omega naught is the frequency of the resulting signal. So a signal with a frequency omega naught is identical to the signal with the frequencies omega naught plus minus 2 pi plus minus 4 pi and so on, right? So how this is equal to this? So let we have a signal x of n equals to j omega naught plus 2 pi into n. So this can be simplified. So we can say e power j omega naught n plus j 2 pi n. Or if we split it, we can say that this is e power j omega naught n, right? And this is also, so this one is your resulting signal. So you understand e power j 2 pi omega naught n, right? Whether it's a plus or minus. So e power j plus minus 2 pi e power plus minus 2 pi n, right? So that's basically, I think, a little mistake. It should be plus minus should be here, right? Plus minus j 2 pi n. So this always equal to 1. If you expand this, so you can write that e power plus minus, right? So either plus or this minus j 2 pi, right? This will be equal to cos of, right, cos of 2 pi, and because it's plus minus, you understand cos is the even function, so when we replace t with minus t, you get the same thing. So that means cos of minus theta equals to cos of theta, and sine of minus theta equals to minus sine of theta, which is sine is the odd function of the time. So uh, it will be something like not time, in fact the independent variable. So if your independent variable is time, then it's a even odd function of time, or right. So this will be j, and this is sine of 2 pi. Okay, so you understand it will always be equal to 0, and this will always be equal to 1 if you have n here, right? So I can put n, and you understand if I put n here, so for because n is integer, so whether it's a n equals to 1, so it will be 2 pi, so sine of 2 pi is 0, cos of 2 pi is 1. Again, if it is 2, then sine of 2 into 2, right, multiple of 2 pi is always 0 in the case of sine, and multiple of 2 pi is always 1 in case of the cosine signal, right? So it will always give you 1. So that means signal having frequency omega naught and those having frequency omega naught plus 2 pi, they are same. So that means discrete time complex exponential, we need to consider a frequency interval of length 2, and we choose the value of the omega naught, right? So that means this is the frequency interval for the discrete time signal. In other words, we can say a discrete time signal frequency is limited to 0 to 2 pi, or we can say this is from minus pi up to the pi, right? So explanation for this is, as we increase omega naught, the frequency of the discrete time signal, from 0, we obtain signals that oscillate more and more rapidly, right? So as we increase it, oscillation increases, right, more rapidly until we reach the pi. After pi, it starts to decrease, and at 2 pi it is same as it was at the 0, right? So low frequencies, that means slow varying exponential, have values near to 0 or 2 pi, and uh, any other even multiple of pi, right? So those are the low frequencies, whether it's a 2 pi, 4 pi, a minus 2 pi, and so on. And high frequencies, which are rapidly varying discrete time exponentials, have values of omega naught which are near to minus pi or plus pi, right? So uh, in the other words, we can say the odd multiples of pi have higher frequency, and even multiple of pi have the lower frequencies, right? So I hope that's clear, that when you move from 0 towards right, so we have more and more rapid oscillations until we reach pi. At pi they are maximum. When we move away from pi, that means from pi up to 2 pi, they start decrease, and they have the same frequencies at 2 pi which are at 0. So that means 0 and 2 pi, and frequency is near 0, and near the 2 pi they are the lowest, or the smallest one, and the frequencies near the pi, they are the highest one, right? And that I think we have done in the previous lecture while we were talking about the uh, periodic signal, right? So for a signal to be periodic, I'm talking about the discrete time case. So a discrete time signal will be periodic when we have something. The relation is this, the period, right? Okay, let's denote it by omega naught. So this will be equal to 2 pi, right, divided by omega naught, which is the frequency of the discrete time signal, times m, which is an integer, right? So meaning to say, if this results into a rational number, if this is equal to rational number, only then we say the discrete time signal is periodic, right? So you understand, for the case of continuous time, the only condition for the period is to be positive, whereas in case of the discrete time signal, the period should not only be positive, but it should also be integer. Okay, so again, like we have discussed for the continuous time case, the relationship between the periodic complex exponential signal and the sinusoidal signal. So again, just like the continuous time case, this is the sinusoidal signal, okay, having the amplitude A, frequency omega naught, and phase of phi, right? So similar to the continuous time case, we can represent the complex exponential signal in terms of sinusoid using the Euler formula or Euler identity. So I think no need for this to explain, right? Because you understand. So similarly is the case of uh, sinusoid. So here it is a cosine uh, function. So cosine function can be written in terms of exponential signal like this. So I hope that's clear. So then the third case, the fourth case that we studied, we talked about for the continuous time was the when both C and alpha, there it was A are complex, when both of them were complex. So you understand, when alpha is greater than, when alpha equals to 1, in that case, this expression, right, because this is just C is the scaling thing. If this is 1, in that case we have just the sinusoids, right? So because cosine, provided that omega naught, the relationship holds for the period, that is we get for the given omega naught, we get the rational value of n, which is period, then this is basically a periodic signal, and that's also periodic signal. So if alpha equals to 1, so we have the periodic, right, sinusoidal complex exponential sequences. So that means, again, to plot this, we need basically two graphs, right? One graph for plotting this signal versus the n, and another graph for plotting the imaginary part, which is this signal. So that's sine versus n, and cosine, yeah, or cos versus n, right? So that will give us the waveform, right? So if again, for generalized case, if alpha is greater than 1, that means this will be exponentially growing signal. So these are the sinusoidal signal. So the resulting graph will be exponentially growing discrete time sinusoids. So if alpha is less than 1, in that case this is exponentially decaying. So this term multiplied by this, so that means the resulting signal will be exponentially decaying times the sinusoids, right? So again, you're very much clear to plot this for either exponentially growing or exponentially decaying. Our sinusoidal case, we will plot use two graphs, one for the real part and one for the imaginary part. So I think that's all for today's lecture, and we'll start the next lecture from this slide. I hope you can go through it, and we'll start from here. I think that's all for today. and see you in the next lecture. Allah Hafiz.